My topic is optimizing a finite element model flagella using RSM, response surface method. So here are some background information. What we know is the exact or the well-known Laplace 2 axoneme structure of flagella. We also know that flagella shows some oscillatory wave-like flagella motion. What we do not know is the exact mechanism that induces this kind of oscillation. We built a finite element model trying to describe this oscillation. So our problem currently is that there are many parameters that are hard to measure experimentally. So I'm going to solve this problem as an optimization problem. I want to get a model that vibrates at a physically reasonable frequency about 70 Hz by tuning or by optimizing these internal and external damping coefficients, as well as the friction coefficients in the model. So here are the proposed procedure of my project. Actually, I followed them fairly well. Basically, I need to design of experiments and then find a response surface and then minimize that so that I can find optimum points, and I evaluate the cost functions at each optimum point. Okay. So the first step is to generate a orthogonal array using Taguchi's approach. So I have 4 original design variables, x1, x2, x3, and x4. This stands for different parameters in my finite element model. And each variable has 3 different levels, so I have to construct 9 sample points to generate this orthogonal array. What I need to do next is to evaluate the function values at each sample point. For example, for the first one, I can build a FE model using these parameters and I simulate it, and here is the simulation result I've got. Okay. And here is a response plot, the midpoint displacement versus time. And from this response plot, using FFT, I can find the vibration frequency of the model. So for this model, the vibration frequency is at about 370. So that's the function value for the first sample point. And I did the same thing for all the other points. Okay, so here's a table summarizing the function values for all the sample points. And next, I need to linearize the notations, linearize my original design variables and assign it a mapping. And then here is the linearized equation. So basically, I was following the techniques described in the textbook. And then I can normalize all the arbitrary linearized variables so that they have a range from -1 to 1. And using equation 20.16 in the textbook, I find the coefficients for the RSM, the response surface. So here is the coefficients vector C, and the W is the inverse mapping from the arbitrary linearized variables to my original design variables. So far, I found the response surface. F is equal to C times W. Okay, so given this response surface, I can minimize it. I can minimize the absolute value between the response surface and my goal, which is 70, to find an optimum point. I ended up using a GA to solve this minimization problem. I assigned 10,000 generations with a population of 1,000, and I ran the GA for 100 times. And 33 times, I found the first optimum point. So x1 equal to 1, x2 equal to 83,000, x3 is equal to 158,000, x4 equal to 2.33. Okay. And similarly, I found some other optimum points given by this GA. Okay. Next, I need to evaluate all these optimum points by FEA. So for example, for the first one, after I ran a simulation, I can find a vibration frequency about 52.9. And for the second one, I found a frequency about 71.1. And for the fourth one, the model does not converge. And for the sixth one, the model does not vibrate. So the vibration frequency is 0 in this case. So even though some optimum points does not converge or does not vibrate at all, I found a very good point, which is the second one. It shows a vibration frequency at about 71.1. I'm pretty happy with that. And here is the simulation result of that point. Okay. I want to call this project a success.